An example of financial portfolio risk and return analysis is presented here. We want to see if we form a sort of a diversified fund of 50% stock and 50% bond, then what would be the average return and the risk in terms of a standard deviation of this diversified portfolio, given the information that I'm going to walk through. And to achieve this, we're going to utilize the correlation coefficient information regarding the involved components and covariance, and also a standard deviation of, let's say, stocks and bonds as the components of investment. Okay, so just as a reminder that when we have X and Y, two different investments, if there is no correlation, we have correlation coefficient R0 as correlation coefficient defined like this, which is basically normalized covariance. Covariance divided by standard deviation of individual components X and Y. And when, of course, there is a negative correlation, like R equal to negative 0.3, then we have this negative trend line, and the dots, or every point of investment in which it has an X and Y value, these dots are sort of spread around the trend line, and as the spread becomes less and less, more compact placement of dots around the trend line. In this example of R equal to 0.5 positive correlation coefficient, we see that there is a less spread, and of course as we get to higher and higher correlation values in terms of absolute value, like 0.9, or in terms of absolute value negative 0.98, the spread becomes less and less around the trend line. So in a separate video, I have already proven that correlation coefficient Rxy is a number always between 1 and negative 1. When you see ρxy and Rxy, we should not be confused. It's the same thing, except ρxy with this formula is the correlation coefficient in terms of the population parameters. Again, normalized covariance, normalized by standard deviation of X and a standard deviation of Y. But when we see the formula below this formula, it's the same concept, except we are talking about correlation coefficients for sample data. So with that in mind, let's just proceed with this example in which we have an investment fund that already has this information that stock fund has an average return, or mu of X, 11%, and a standard deviation, or sigma of X, of 23%. So that information we already know. And aside from that, the same thing for bonds and for real estate fund. So for these funds, the information for average mu, or expected value, and a standard deviation is available as listed in this table. In addition to that, we are also informed that the correlation coefficient, which is basically this value or this value, doesn't matter in terms of concept, between the stocks and bonds. So I'm going to highlight it here. So correlation between stocks and bonds. So it means between these two components. And between stocks and real estate, it means between these two components. And between bonds and real estate, so this time between these two investment component options. So these correlation coefficients available, you can see that the value for the correlation between stocks and bonds, which historically is a negative value, is in this example, hypothetical example, negative 0.48, 0.58, and negative 0.15 between bonds and real estate investment. Okay, with this information available, with this information, then can we compute the average return or expected value, EV, or mu of it, mu of, let's say, the formed linear combination, or let's say mu of return, or the formed portfolio, mu of P, and also a standard deviation of P. So we are forming a portfolio as an example for the first line here, in which we are saying portfolio is equal to 0.5 stock plus 0.5 bond. And the question is, what is expected value of P, or basically mu of P? What is it? That is the average return in percentage or percent. And what is the sigma of P? That is the risk or standard deviation. So to find that, let's just remind ourselves that any linear combination of two random variables like S and B, which are the returns of investment in a stock and bond in the form of A, let's say AS plus B, let's say, let me put it this way, aX plus by, like the x and y that are shown in the x and y axis here. We know that obviously, so let me make sure that, okay, so we know that obviously mu of p, or expected value of p, is simply a mu of x, or expected value of x, plus b mu of y. Sometimes you see people write it as also this way. So sometimes you see it's written this way, that p bar is equal to ax bar plus by bar. That is in the context of sample data, which is fine. I mean, it's the same concept. Now, sigma p, or sigma square, let's say, variance of p, is equal to a square sigma square of x, which is the variance of x, plus b square sigma square of y, which is the variance of y, plus 2 times a times b sigma xy, which is covariance of x and y. So this is already well known and proven, so we're going to just directly use it. Okay, so in the first problem, you can see that a is 0.5 and b is 0.5 as well. So we're going to just substitute. Therefore, because of the information provided, we can say mu of p, or p bar, if you want to name it that way, is 0.5 for a, mu of x, which is mu of basically s, because x for us is the stock investment return, and b is 0.5, and mu of y for us in the first line is bonds. So y is bonds, and x is a stock, and these 50% are the a and b. So mu of bond. Okay, we're going to use the information in the first table. You can see that for a stock, average is 11%, so it's 0.5 obviously times 11%, so times 11, plus 0.5 times 11, for mu of b is not 11, for mu of b is 4.5. So when we compute this, of course, we get 5.5, and then we get 2.25. So we get 7.75%. So that is the average return for the diversified or combined portfolio, which is a equal weight linear combination of stock and bond. Now, for sigma p, which is the risk for standard deviation, let's first compute variance of p, and then after that we can take a square root. So variance of p using the formula that is presented here, we can just simply say it is, again, substituting a square is just 0.5 squared, and then sigma square is the variance, which we go to the table for x is sigma square of s, which is our 23%. So it's going to be 23 squared, and then we get plus b squared, which is 0.5 squared, and then for sigma y squared, we have, let's say, 4%. So it will be 4 squared, and then finally we have 2 times 0.5, that is a, 0.5, that is b, so I'm talking about this portion, and then finally sigma xy. Sigma xy, we don't have it directly, but we know sigma xy, this component. So we know, using this formula on top, sigma xy, as you can see, let me expand it, this formula. So sigma xy is just rho xy times sigma x sigma y. So I'm going to substitute for sigma xy using sigma x sigma y times rho xy, or correlation coefficient. Now it's as before. Sigma x is sigma of a stock, 23%. Sigma y is sigma of bond, 4%. And rho xy is correlation between stock and bond. So stock and bond has a correlation of -0.48. So we can easily compute this. If we do so, we are talking about 50% points, so I have already plotted things here in terms of average return and expected value for diversified fund in the sense of, let's say, portfolio. Let me write it here. So portfolio is let's say A times stock plus 1 minus A times, because either you put your money in a stock or you put your money in bond. So that's it. And A is on x-axis. So you can see that when A is 0, all the money goes into bond. And therefore, as a result, the return of the whole portfolio, because everything goes to bond and nothing goes to stock, the return of portfolio becomes exactly return of bond, which is 4.5%. And when A goes to 1, everything goes to stock, and therefore the return of overall portfolio becomes exactly the return of stock, which is 11%. So, and then for the 50% point, as the example here, you can see that the return is around 7.75, as indicated also here. So this point is 7 point, as we found. And for sigma p, so I didn't compute it, but if we continue, sigma p is just square root of sigma square, or variance. And that value, when we compute this thing and we take a square root, that value is what is reported in the lower plot. So again, for the lower plot, the x-axis, let me just make sure that I'm not missing something. Okay, so for the lower plot, the x-axis is A, and the y-axis is percentage in terms of return. So when A is 0.5, as in this example, 50% distribution of money into stock, 50% into bond, you can see that effectively the overall standard deviation is trending toward something like 10 point something, 10.5-ish. So I would say this number is roughly 10.5%, roughly. So you might deviate 10.6 or something, but basically standard deviation of portfolio trends toward 10.5% for 50%. So that's much better than the original number. See, the original number, we had 4% standard deviation or risk for purely bond and 23% for purely stock. So now you're getting a return of nearly 8%, which is halfway between these two values roughly, but at the same time we are getting a risk of about 10.5%, which is much better than the 23%. So it's a good compromise. Rather than getting gain of 11% by fully putting the money in stock, we are getting a gain of less 7.7%. So let me highlight it. So this gain, 7.7%, I'm going to highlight it with different color. This gain. But then for that compromise, we are getting a much better standard deviation or risk. So risk is much lower compared to risk of a stock. So it's a good compromise. Now you could do this for other distribution, like for example, take a look at 70% stock and 30% bond. So if in that case, the A here for a stock will be 70%. So you're shooting for this. And as you can see, when you do that, then the return goes higher because now you're putting more money into stock, which then return turns out to be around 9%. So I'm going to put it here. Here we found it's 7.75. Then we found around roughly 10.5%. Here we found the return is now 9%. But if you look at the standard deviation, now standard deviation is considerably increased to around maybe 15.5-ish when you look at this dot. So I'm going to put roughly, again, you're more than welcome to calculate yourself, but I'm going to put roughly 15.5%. Okay, so you can play the game going with the last row, which is 30% stock. So with that, A will be 30%. And if you redo this calculation as I showed here, except that now A is 0.3, and of course, as a result, B, which is 1 minus A, is 1 minus 0.3 is 0.7. So effectively, our portfolio here, A and B, becomes 0.3x, which is a stock for the last row, plus 0.7 bond. And for that one, we are saying A is 0.3. And if you go up, you can see that now you're talking about 6.5% roughly return. So yes, return goes further lower, 6.5%, because now we are putting more money into bond, which is lower return, but then standard deviation considerably goes lower. So if you take a look at 0.3 here, you can see standard deviation of this dot is trending towards 6% roughly. So I'm talking about 6% here. Okay, I'm talking about 6% here, which is considerably lower. So all the thing that this table is trying to show and show you is indicate that depending on your taste, on investors' taste for or appetite for risk, then we can form a different linear combination in terms of what portion of money goes to, say, stock, what portion goes to bond, so that we adjust our expectation for let's say, return, average return or expected value, and then, as you can see in this column, and then correspondingly, the risk will be adjusted as well. So as you can see, for instance, 30% stock, 70% bond give us roughly 6.5%, while 50% bond and 50% stock also give us 7.75 in the same ballpark. But risk is substantially reduced compared to 10.5%. So see, sometimes a little sort of a considerable adjustment in terms of allocation of money doesn't change the average return that much, like for example 7 to 6, but then the risk substantially goes lower or higher. So we need to be careful about that. With the same technique, we can also compute 50% real estate and 50% bond. It would be basically a repeat of this computation shown here, except we have to plug in numbers for bond and real estate. So we're going to plug in these numbers to our calculation that was shown already for 3 other examples. I hope that the combination of this example and this plot that sort of indicate and show, maybe the last thing I want to show here is, as you can see, this plot nicely shows that at the beginning, when everything, when A is 0, all the money is going to bond, and therefore we are getting the risk of bond, which is 4.C. The risk of bond is, the standard deviation of bond is 4%. And as a result, you can see that at the beginning, when A is 0, everything is going to bond, we get 4%. But then, because of negative correlation between bond and stock, as we are increasing the proportion A from 0 to, let's say, 10% into stock, 90%. So this means 10% in stock. This means 10% in the stock, and then it means 90% in bond. So 10% in the stock. You can see that despite the fact that our contribution of money now is not 100% in a stock, and as a result, our return is now, instead of initial 4.5, is 5 point something, so improved. But then risk further even went down, because of that's the benefit we get from the negative correlation between bond and a stock. But gradually, as we start going toward 20% contribution to a stock, 80% bond, we get a better and better risk, of course, better and better return in terms of annual percentage return, getting close to 6 and 6.5%, but then risk started going up. So, but it indicates that 20% allocation to a stock versus 0% allocation to a stock has roughly same risk of 4%, but then considerably larger return, around 6% versus originally 4.5%. I hope that this example is helpful in terms of illustrating how, a simple example, how allocation for the diversified funds or mutual funds can be done to maximize return and minimize the risk or standard deviation.